Okay, so let's get started with today's laboratory run through. Today we're going to be looking at Chem 100 Experiment 7 concerning electron configurations and periodic properties. So first and foremost, let's talk about where to find today's laboratory page and where to find the laboratory pages in your lab manual. So first and foremost, in Canvas, Experiment 7, Electron Configurations and Periodic Properties, is found in the Canvas laboratory modules. There is a laboratory page available, and that laboratory page is going to contain the videos, images, and other information that you need to write down and record your data and observations for this experiment, and then ultimately complete the calculations and complete your report sheets to complete this lab. So looking at the lab page, the experiment 7 lab page looks something like this in Canvas. Let's also open up experiment 7 in the lab manual. So this is what experiment 7 looks like in the lab manual. It's titled Electron Configuration and Periodic Properties. And there's a general set of lab information as well as some introductory pages found in the lab manual. We'll be talking about that momentarily. If you need additional information on the background or theory behind today's lab, I would encourage you to review the pre-lab lecture recordings, and there is one available for Experiment 7, where I talk through and discuss a little bit of the theory behind today's lab. Okay, first and foremost now, as we are working to complete this laboratory, again, looking at the Experiment 7 pages in our lab manual. If we scroll down, there's some very important background information. So this contains a lot of information on the theory behind this lab, how to write electron configurations, what does an electron configuration represent, how do you write a box diagram, etc. So there's a fair amount of background information that I would encourage you to read. If you need another source of information on electron configurations, I would encourage you to reference the course notes and the course lecture recordings as I cover this topic in detail as part of the course lecture content. There's also some discussion of atomic radius and periodic properties. We now move on to the experimental procedures, which we'll address as we work through today's lab. And if you continue to move through the lab pages, I would like to draw your attention to this table provided. This is table 7.1, which has the list of each element along with its atomic number and atomic radius. Please make a mental note of this table, and please just note in your own personal lab manual, you want to be able to find this table again as it's used as part of this laboratory to complete one of the later report activities. So just make a mental note that this table exists and it's found in the lab manual. Okay, we now move on to the report sheets. As always, we have the pre-lab study questions, which we can skip for today. And now we have the main report sheet. So I've taken the liberty of transferring the report sheet onto the virtual notebook. So we have the full set of report sheets, and we'll be working through this lab together today and filling in the report sheets with the required data, and then we'll complete any required calculations and answer any questions posed by the lab report questions as we encounter them. Okay, so in order to properly contextualize what is being presented to us in these report sheets, let's read the lab procedure. So let's read the lab procedure. So we're working on part A, as that's the first part in this lab. So let's take a look at part A. So part A concerns flame tests. So in this case, we would, if we were working on this lab in person, we'd obtain a spot plate and a flame test wire. We would clean the flame test wire. We'd then place 6 to 8 drops of the test solution into the spot plate. And in turn, we label where we put each of the solutions in our spot plate. From there, we generate a reasonably strong Bunsen burner flame. And from here, we're ready to begin observing the flame emission colors. So in this case, if you place a solution of a metal ion in a flame, that in turn excites the electrons found in each metal ion, which leads to transitions between energy levels. And as those electrons return to the ground state, light is released. And this light emission, the flame color that you observe, is characteristic and unique for each metal ion, and it can be used to identify what element is present in a solution. So it's quite a useful test. If you've ever seen, for example, a firework, a lot of the unique colors that you observe in a firework show is a result of the atomic emission spectra of a given element. So in this case, we take the cleaned wire, we dip it into one of our metal ion solutions, and then we place that metal ion solution into the flame. We'll observe the color of the resulting flame, and we can use this information to assign and determine the identity of a metal ion in a solution. So we're going to be doing the flame test for a series of known solutions, and then we're also going to identify an unknown solution by observing the flame test colors for those unknown solutions and then matching the unknown solution to one of our known solutions. So in order to collect this flame test data, I have provided you some recordings to review in the Experiment 7 lab page. So again, there's some introductory information. We're going to scroll down all the way to the experiment procedure. So part A, flame tests. So in this case, I prepared some videos. You're going to watch these videos and you're going to record your observations for each flame test in your laboratory manual. You're also going to note and record the observations for the 3 unknown samples. From this, we're then going to assign the identity of each of the unknowns by comparing the unknown flame colors to the known sample flame colors. Okay, so I already have pulled up the first video, and this video showcases the flame test results for strontium chloride, sodium chloride, potassium chloride, lithium chloride, copper chloride, and calcium chloride. Okay, so let's look at our table now. For the spot plate diagram, you can just leave that part blank. And just note that we don't have to fill in this part because we're not actually preparing a spot plate. But we now see that we have a table and we're looking at the flame test results for a range of different solutions. So let's watch the videos and let's fill in this table. Okay, so this is a classic flame test video. So they have a range of labeled solutions, and we're going to be taking these solutions and placing them into the flame. So I'm just going to skip ahead a little bit, talking a little bit about the experiment, and now let's move on to the actual demonstration. So they have a Bunsen burner flame set up, and let's pause here and note that they are starting with the calcium chloride solution. So let's observe and carefully record our observations for the calcium chloride flame test result. Okay, I'm going to pause this here. So as we can see very clearly, a unique colored flame is observed when the calcium chloride solution is exposed to the Bunsen burner flame. In this case, we'd record the color. So for calcium chloride, I'd record the color of the flame as red. Okay, let's now continue on. Okay, calcium chloride. The flame test is still ongoing. As you can see, you can observe a clear and unique flame color for each clear and unique ion. Okay, the next one that they're looking at, as noted by the label, is a copper chloride sample. You can see based on the label. And just to pause one moment, we again can observe a characteristic flame color. As you can see in this case, the copper chloride results in a characteristic green flame. Okay, let's keep going. You will also commonly see this green flame if you have not properly cleaned your glassware. They're moving on now to lithium chloride. So let's take a look at lithium chloride. So in this case, for lithium chloride, we could clearly see, let's just go back a moment, a red flame. Lithium isn't on the list here, but I feel it's important to show that this effect isn't just limited to the metal ions that we're looking at as part of the lab manual. You can also look at other metal ions and observe similar unique flame colors for unique metal ions. Okay, let's keep going now. We're now moving on to potassium chloride. Potassium, let's pause here. Potassium is a little bit hard to see, but it's sort of a purple magenta colored flame. So we'll note that. And of course, part of the reason why I set this up with videos is if you ever miss one of the observations, you can go back and rewatch the video. Okay, so that's potassium, purple magenta colored flame. We're now looking at sodium chloride. So looking at the emission spectra for sodium. And as we can see, it's a characteristic yellow flame color. Okay, let's continue on now. Now for strontium, this will be pretty dramatic. So as you can see, for strontium, we observe a pretty clear, bright red. Strontium is commonly used in road flares. It also can be used in fireworks, and it has a pretty dramatic atomic emission spectra, as you can observe by the brilliant red flame observed. Okay. So with that, they've concluded this demonstration video. So let's look at a second video because we still have some parts that we have to fill in. And the reason why I like this second video is it lets us cross-compare results. So this video has the results for strontium, barium chloride, as well as a repeat of sodium, potassium, lithium, copper, and calcium. So let's just take a look. Potassium, as we can see, that very characteristic purple-violet flame. Okay. For barium, let's see if they do another attempt for barium. Let's go back. So for barium, okay, we observe a green/yellow flame. It's not quite as green or yellow as for copper or sodium. It's almost at the middle point. You can also call it pale green, as you can see from this flame color. You can also say pale yellow. more than reasonable. As you can see, we can clearly distinguish barium from something like sodium, where for sodium, as we'll see, it's closer to like a yellow-orange color. Again, this is all very qualitative in nature. Just make sure you take your observations, and if you're ever unsure, you can rewatch the videos and even compare the two ion flame colors side by side, and you'll be able to see the differences. Okay, so barium, we filled in that portion of our table. Now we're looking at some repeats. Calcium, as we've seen previously, has a red-orange flame color. Strontium, as always, has the brilliant red flame color for its flame emission spectra. Again, we're just reconfirming our past observations, making sure everything lines up. Lithium, a red flame emission. And sodium, which is more of a yellow-orange. It's quite a brilliant color, clearly distinguishable from barium. Copper, we would expect to be green, as we observe. It's always good to have multiple sources, multiple trials for these flame tests, so that way you can verify that your observations are consistent. Wonderful. So we've viewed these videos and we've filled out our table. Now that we have our observations for the known samples, let's look at the unknown samples. So I provided you a table, unknown 1, 2, and 3. Unknown 1, we noted had a purple flame. Unknown 2 and 3, let's just record from this table. Unknown 2 had a green flame, and unknown 3 had a yellow-orange flame. So I'm going to do the first one of these unknown identifications, and I'd like you to assign the other unknowns independently. So just to show how this would work, I see unknown 1 had a purple flame. I see only potassium has a purple flame. So unknown 1 is likely a solution of potassium chloride, and thus it contains potassium. You'll assign the identity of the other two unknowns, and you'll also answer this post-lab question. Let's now move on to part B, as we completed part A. So let's see what part B entails. So let's open up our lab procedure. So in this case, we're asked to write the electron configuration of each atom listed, indicate the number of valence electrons, and determine the group number. Okay, I'm going to do the first one of these as an example, and you'll complete the remainder of these electron configurations independently. So in this case, for oxygen, so oxygen has an extended configuration of 1s2, 2s2, and let me pull up the periodic table just to make sure. So let's see if we have a copy of the periodic table. We do not have one available in this portion of the lab, but that's okay. We do have a periodic table available. I'm going to pull up a copy of the periodic table and reference that. So allow me one moment to pull up a copy of the periodic table. So in this case, for oxygen, it would be 1s2, 2s2, 2p4. You can also write this as helium, 2s2, 2p4. The valence electrons are the outermost electrons with the largest principal quantum number. So in other words, these 6 electrons are considered our valence electrons. So we have 6 valence electrons, and the group number for oxygen is 6a. As a quick sanity check, you can always identify and double check your valence electron count. As for main group elements, the number of valence electrons directly matches the group number. Oxygen's a 6a element, and thus it has 6 valence electrons to its name. So we've completed this initial example. Let's do one more just to make sure everyone understands how we're writing these electron configurations. And let's do an example in this case where we are dealing with a transition metal element. So let's look at iron. So if we look at iron in the periodic table, iron has 26 electrons to its name. Iron is also in the 4th row of the periodic table. So let's start by filling in our electron configuration. So we fill the lowest energy levels first. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we're now in the transition metal block. We are 1, 2, 3, 4, 5, 6 spaces in the transition metal block. So this would be a 3d6 configuration. We could also, using abbreviated electron configurations, abbreviate these innermost electrons as an argon noble gas core, and then write out the remaining configuration as 4s2, 3d6. In terms of the group number for iron, it's labeled with an 8b group number. The B just denotes we're in the transition metal block. In terms of the valence electrons, in the case of iron, and in the case of transition metals, you can treat the d electrons as if they are valence electrons, as they can be easily lost during ionization, etc. So in this case, if we count up our valence electrons, we can note that we have 8 outermost valence electrons available for iron. This is something unique about transition metals in that transition metals can lose their d electrons during ionization. To provide a contrast, let's look at bromine, which is also in the same row as iron, but this time we have 35 electrons to work with. So in this case, for bromine, we can abbreviate the configuration as argon, 4s2, 3d10. We've completely passed the transition metal block, followed by 4p5. So in this case, because bromine is a main group element, and because we have these outermost 4s and 4p electrons that are much easier to be lost during ionization, and those electrons and those orbitals are much more available and accessible for bonding. If we're counting the valence electrons for an element such as bromine, where we've completely filled out the 3D shell. We don't really view these 3D electrons as valence. They're pretty difficult to access, and they aren't pretty relevant in terms of bromine's reactivity. So counting our outermost electrons, the electrons with the largest principal quantum number, for bromine, we conclude that there are 7 valence electrons, matching its group number of 7a. Let's move this over. So bromine has 7 valence electrons, a group number of 7a, and thus it would have a configuration of argon, 4s2, 3d10, 4p5. You can also write out the full extended configuration if you prefer, which for bromine would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Both configurations are valid. I just find the abbreviated configurations are much easier to write and much more compact. They also more readily show the innermost and the valence electrons, because when you write an abbreviated configuration, usually whatever electrons remaining that you're writing out are the valence electrons. Okay. Again, if you need any background information on writing electron configurations, I would encourage you to reference the pre-lab reading as well as the course lecture notes and lecture videos. Importantly, you're going to want to have a copy of the periodic table available, and that is found in your lecture textbook and in your lab manual as well. There's also one available in the lecture notes. So we've done some representative examples for part B. Let's move on now. There are some questions that you'll have to complete, and you'll be working through these questions independently. Finally, we have this graph, and let's read part C to figure out what we're doing with this graph. So for part C, the atomic radius for elements with atomic numbers 1 through 25 are listed in table 7.1. So this is the table that I asked that you remember and make a note of, as we'll be using it to complete part C. So on the graph, we're asked to plot atomic radius versus atomic number. And be sure to connect all the points. We'll then use the completed graph to answer questions in the report sheet. Okay, so what I'm going to do now is I'm going to just put this data table right next to the graph. Okay, wonderful. So now what I'm going to do is I'm going to start generating my graph axes. So I need to get a sense of, for the first 25 elements, what is the largest atomic radius that I'm going to encounter? So in this case, if we look at this table, the upper bound is going to be about 230 to 235. Now, I'm going to count the number of squares that I have in my table. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Well, that's convenient. I can just make each of these marks 10. $10, $20, $30, $40, $50, $60, $70, $80, $90, $100, $110, $20, $30, $40, $50. $60, $70, $80, $90, $200, $210, 20, 30, 240. Okay, perfect. So we're making sure that our graph data points encompass a fair amount of the graph that we're generating. So now we're just going to plot our data points. So atomic number 1 has an atomic radius of 37. Okay, atomic number 2 has a radius of 50. Atomic number 3 has a radius of 150. And as you notice, as we move to a new row in the periodic table, as we move from the first row to the second row, the atomic radius increases dramatically. We'll see if that trend repeats itself. So continuing, we plotted beryllium, now boron. Okay, carbon. Now for nitrogen, oxygen, fluorine, neon, and sodium. Okay, magnesium, aluminum, silicon, phosphorus and sulfur, chlorine, argon, potassium, which is going to pretty much go to the top of the graph. Again, we can notice a bit of a repeating pattern here. Almost like there's some, that these trends repeat itself over a defined period, in that as we move to a new row or period of the periodic table, we observe similar trends of atomic radius as we move across a row, across a period in the periodic table. Okay, let's finish up this graph. So we have calcium, scandium, titanium, vanadium. So calcium, scandium 160, titanium 150, vanadium, chromium, and manganese. Okay, now let's connect the lines as best as we can. So not the best artistic depiction, but nonetheless, we're able to see a very clear trend where as we move to a new row, the atomic radius increases dramatically. And then as we move across a row and the number of protons that we have in our nucleus increases, the atomic radius decreases as we move across a row in the periodic table. Wonderful. So now we have a graph and we can use that graph to answer some of the post-lab questions. So in this case, we're asked to describe the change in atomic radii for elements in period 2 from lithium to neon, and then answer why does the change for the atomic radii of elements in period 3 from sodium to argon look similar to period 2? For that, I would encourage you to take a look at the number of valence electrons found in the row 2 and row 3 elements and see if you notice a trend. And I would encourage you to reference the pre-lab readings as well as the course Canvas page for experiment 7 to help you answer these questions 4 and 5. I'd like you to answer these questions independently now that you have a full, complete, and accurate graph of atomic radius versus atomic number in hand. So with that, we have completed experiment 7, electron configurations and periodic properties. Again, remember to turn in all of your completed report sheets to the lab submission page on Canvas. As always, these example report sheets, as well as this lab run-through recording, will be available on Canvas for your reference.